am happy to try to answer questions about the homework assignment. If you have them for me, would it be super useful for me to display the homework assignment up here?
Yes.
Okay. Maybe while I'm setting up, I can try to do two things at once. And if you want to throw some verbal questions at me, maybe simple questions to begin with, simple verbal questions, I can try to answer those while I'm getting this set up.
So when you say that use the noise figure to find the total amplifying and thermal noise, we already calculated the thermal noise. So it's just based on the addition of those two, or the SNR and over equation.
So as we went through that algebra, what we found the other day was that the noise figure is basically the ratio of the thermal noise plus the amplifier noise divided by just the thermal noise. So for example, let's say hypothetically your homework assignment said the noise figure was 3 dB. That's roughly a factor of 2 in power. And so it would say that thermal noise plus amplifier noise is twice as big as just thermal noise, which in other words implies that amplifier noise is the same the same amount of power as thermal noise. And remember, when we're adding those noises, that we're always adding them as the square of a current or the square of a voltage so that they're proportional to power. Does that help answers that question?
Yeah.
Okay. Yeah. If anybody wants to rewrite my questions for me, I'm perfectly open to.
Oh yeah, question 2 plus 2.
Because that's really getting to the heart of the same thing that the language I constructed was about. Say that again one more time, please.
So in 1G, you said
Right, so I think in the problem what I told you was that the resistor that is the source of the noise is this 20 megohm TIA resistor, and that we can just ignore all other sources of noise in terms of the amplifier and just claim that that is the source of the thermal noise. And then in that configuration, if the noise figure were 3 dB, what we would get is, based on what I just said, is that the thermal noise, mean square thermal noise associated with this is going to have the same amplitude as the mean square amplifier noise because it's 3 dB for the noise figure. More generally, the noise figure is going to be equal to the sum of these two divided by the thermal noise. Does that answer your question?
Yeah.
Okay. So far, I'm handling questions just fine as long as you don't expect any progress on my laptop. Any other questions that you have?
On the last one on 2E, just wondering if I'm reading this right, it gives us an SNR and we backwards solve for the molecules.
That is the idea, yes. Okay. So you get, do I give you an SNR or do I tell you a value of K and say that you're at the limit of detection?
Yeah, you give us a value of K, then the SNR at the limit.
Okay. Right, and so from there you figure out how many molecules you need to reach that.
Okay.
When I change the number of molecules, does that change any of the noise in the system?
Good.
What type of noise would it change? Okay, so what is the source of thermal noise? Right, so when I change the concentration of molecules, is that changing? No. I don't think thermal noise changes with the concentration of molecules. Why would it change the shot noise if the concentration changes?
The shot noise is related to
Right.
if you have a lower voltage.
Right. And perhaps just because of my training and thinking about photodetectors, I usually think of photodetectors as a source of current as opposed to a source of voltage. And so remember our formula for shot noise is that it's equal to 2 times the fundamental charge times the average current times the effective bandwidth. And so if I change the concentration of molecules for the same level of pump excitation, I'm changing the amount of fluorescence signal coming off, the power of fluorescence. Makes sense, everybody? If I change the amount of power of fluorescence, I'm changing the current that comes out of the photodetector. And if I'm changing the amount of current coming out of the photodetector on average, I'm changing the amount of shot noise. So in that problem where I'm asking you to try to get to a particular signal-to-noise ratio, the concentration isn't just affecting the signal. It's also affecting the noise. And that's why you end up with a quadratic equation that you need to solve. Okay? By the way, for those of you who are only here to get your 1 credit in Escape and don't care anything else about biosensors because you're communications jocks, same basic story goes on in communication. You talk about what the power levels of the signals are in fiber optic communications, how strong that signal is affects the shot noise level, and has an influence that way. All right, if I yak long enough, I won't even have to pull this thing up. Any other questions on the homework?
So the delta F that we used in part B, is that the delta F that we calculated earlier, or is that the sum total of all the shot noise from the one?
So delta F is the effective bandwidth, the noise effective bandwidth of the system. So before you put the low-pass filter on, what is the effective bandwidth that the problem tells you to use? Yeah, and I should think about how I worded that. What did I say 10 kilohertz was? Did I use the word noise in that? The noise bandwidth. Okay, fine. So you get to just multiply delta F straight out there on the end of the equation like that. And then, because a million or whatever it is was not a high enough signal-noise ratio, I'm being sarcastic here, I decided to have you filter it so you could get a higher signal-noise ratio. And you calculated some filter bandwidth, and then to figure out how to relate, if I have a simple RC filter, and I should explain some of the terminology. There's a formula in there that has VC minus VN. Yeah, VC minus VN. So this is plus, this is VN. I should have probably called this V out, but I labeled it as VC. Those are the same thing, VC and V out there. And you go through and you figure out basically how narrow, how low of bandwidth of a filter you can use without messing up the time constants of the signal by any more than 1%. And by the way, there's a reference to an extra credit problem. I didn't actually give you the extra credit problem, okay? I just gave you the result. And then once you figure out your bandwidth, so let's say you go through and you figure out you want a 3 dB bandwidth of this of 40 hertz. How do we get from that to knowing what the noise bandwidth is? What's our expression for the noise bandwidth of a single pole filter? Go ahead and scream it out like you believe it if you know it. Yeah, it's 1/4 RC or 4 tau, effectively. So this is equal to 1 over 2 pi times tau, whereas the noise equivalent bandwidth is equal to 1 over 4 tau. So just make sure you're making that adjustment between the 2 pi and the 4 when you're doing the noise calculation. And tau in that case is referring to the RC time constant of the filter. Okay. I'm almost ready to go start looking for this assignment now. Any other questions?
Towards the top question. Okay, what is the maximum average voltage?
Well, would noise affect the maximum voltage?
Yes.
Because it has these little spikes sticking up on it, right? And so if I wanted to ask you for the true instantaneous ever maximum voltage, you'd have to predict what the biggest noise spike would be, which you can't do absolutely. Maybe you could talk about it statistically, okay? So I'm saying, so my wording of average maximum, although it's a little confusing, means to imply forget noise. What is the maximum signal you would see in the case of a noiseless system?
I also applied in DC when you what is rest as a mean square voltage.
Yes. I had ENS come over and work on my computer for about a half hour yesterday to try to make this screen not screw it up. So it'll be interesting to see if we made any progress. Any other questions on this assignment? By the way, I have problem number 3 half written. I do need to post the solution to number 2. I'm hoping to do that soon after class today. Any other questions on this? Any other questions about anything else that we've covered up to this point that you want to discuss?
So the equation that you have up there for the voltage of the shot noise isn't that the equation for the current square voltage or mean current? The mean square current of the shot noise.
Yep. Sorry about that. This should be current.
So in order to change that to voltage, would you then just think of it as power and then have instead of I average, you have the average over R?
So we have an amplifier that's a transimpedance amplifier. Why do we call it transimpedance? What are the units of gain for our transimpedance amplifier? It's volts over amps, right? It outputs volts, the input is current is amps, which in case you've forgotten happens to equal ohms. And so the gain is given in resistance. In fact, this right here is the gain of the transimpedance amplifier. Transimpedance amplifier is a common design, is something that looks like this. And you might put the photodiode in this way, or you might even bias this to some negative supply voltage, and the light's hitting it. So really the amplifier is just there to force this thing to obey the equations, okay? The magic Dorito in Zach Black's terms, it's just there to make it obey the equations. And you can just think of it as pulling this amount of current through that TIA resistor. And so if I want to convert this, if I do want to calculate the mean square shot noise as a voltage, and I'm thinking about it as a current noise that's flowing right there, how do I convert that to a voltage that's appearing out here at the output? This is a simple question. I only ask ever simple questions, as you can tell from my homework assignments. So what do I do to get from here to here?
Put that on
Do I multiply by R, divide by R, multiply by R squared? R squared. Not just R, but it's R squared in order to change from current squared to voltage squared. So make sure that you're using the square of the resistance in that case. Does that answer that question, Jacob?
But so then the I average that we would be using the total.
Right. So there's, in addition to the contribution to average current that comes from the fluorescence, there's also the dark current. And you would want to include the dark current in that effect. All right. Any other questions? So when is this homework assignment due? Remind me. Thursday. And are there extensions this time around? And am I going to post the solutions soon afterwards? Yeah, that's what I told you. Okay. I don't have to do anything anymore. You filled out your course surveys. I'm just kidding. That's the goal. All right. Anything else that you guys want to talk about before I launch into a last little bit of material? All right. Let's see if I can get my...
I know that we covered SNR in class. When I try to find it on the lecture notes, is it, can be able to post those as well?
Yes. I will post the SNR slides, and I will also post today's slides. So let's talk about something that may be a little boring for you. Quantization noise. How many of you have talked about quantization noise and A to D converters before? Okay, a little of you, a few of you. Sorry, I didn't mean to say a little of you. You're all very important and big. Just a few of you big, important people. So, again, remember these slides are meant to be interpreted by biologists also. So we'll go through this quickly. You guys know what analog to digital conversion does. It's nearly ubiquitous nowadays. What's the last time somebody actually used a truly analog instrument in here to measure something? And what did you use it for, Tom?
To just measure the output from a comparator.
And what, you did it with a meter?
No, just with the analog oscilloscope.
Okay. How old is the analog oscilloscope?
It's got to be probably at least
Okay.
Jesse.
I see. So some people have historic artifacts in their lab that they're having students work with. Okay. Somebody else? What did you do, Zenon?
I used one of the dial voltmeters from
Oh, really?
Yeah.
And you trust the old analog meter more than the DMM?
Well, it was a Harper Freight meter.
Oh, yeah.
Yeah.
I get my students to buy my ECE 204 students to get those for free for class, and they're worth every penny they pay for them. So it's really kind of interesting. They have a dog leg on the printed circuit board in there, and when you plug in the high current probe, it snaps the circuit board most of the time. So you have to be very, very gentle with those. At any rate, almost everything's digital. Almost all analog to digital converters digitize voltage as opposed to current. They may have an amplifier that converts current to voltage before it digitizes it, but in terms of the A to D, it's almost always digital. We're going to say that they output 2 to the n values, where n is the number of bits. We usually think about there being some type of limited range for the A to D conversion, somewhere between Vmin and Vmax. If Vmin and Vmax have the same sign, like Vmin is 0 and Vmax is plus 5 volts, we'll talk about that as a unipolar analog to digital converter. And then there's also bipolar ones, such as -1 to +1 volt range. The resolution then we can figure out is Vmax minus Vmin divided by 2 to the n minus 1. Why minus 1? How many segments are between 3 points? 2. So if it can measure 4 levels, then it can only have the distance between this point and this point is 3 times the interval. So that's why the -1 is there. And so, for example, if I have a 5-volt analog to digital converter that's 8 bits, it has a resolution of about 20 millivolts. Okay. So, because there's only a finite number of levels, but potentially continuum, an infinite number of possible input voltages, we cannot perfectly represent with the output of an analog to digital converter, here a 3-bit analog to digital converter, all the possible input voltages that go into it. So there's going to be some small error. We'll use epsilon to represent this error, which we call a quantization error. And the quantization error depends on exactly where the input voltage is. So if I have precisely some voltage that is the connection between the mapping of these lines here, like this point right here, I would have exact quantization and there would be no error in the signal. But if I'm, say, over here where this blue line is, and what I'm getting out of it is a 0, 1, 0 representing that particular voltage level, when the real input is up here, I have a quantization error that's almost half a step size, and that's what epsilon is. So the error actually depends on precisely what the input voltage is. And if you subtract the red curve from the green curve, and then you integrate over some set of evenly spaced set of bits here, you'll get a sawtooth wave, all right? And when you integrate that sawtooth wave, if you try to find what the mean square error is, you're going to find out that it's equal to this expression here, which is basically the quantization interval, this delta V, such as the 19.6 millivolts we just mentioned on the last slide, cubed divided by 12. So the quantization error actually goes up pretty fast as you get to coarser sizes. It goes up as the cube of the quantization level. So for example, let's say that I move from an 8-bit analog to digital converter to a 10-bit analog to digital converter. How much does the mean square quantization error or quantization noise go down? Went from an 8-bit to a 10-bit. So what happened to delta V in that case? Went down by a factor of 4, right? Because I added 2 more bits, I took delta V down by a factor of 4. And so if I decrease delta V by a factor of 4, I decrease delta V cubed by a factor of 64. So adding 2 bits to an analog to digital converter will actually reduce the noise level down by a factor of 64. And for this reason, people love to go buy 16-bit analog to digital converters. Now, you should ask yourself, are all those extra bits really doing anything for me? So for example, if thermal noise completely swamps out this quantity already, then maybe it's not worth spending the extra money on the extra bits. Any questions about this slide in terms of what the cause of quantization error is or how we're defining it? Okay. So let's talk about the maximum signal-to-noise ratio we could ever get based on quantization error for kind of a randomly distributed signal. So first of all, what's the biggest possible signal I can get out of an A to D converter? Well, the biggest possible mean square voltage for the signal I could get is if this thing was going from Vmax to Vmin or pretty close to that, jumping back and forth. And so the biggest signal I could possibly get is just that full range squared, Vmax minus Vmin squared. What's the best error? What's the lowest quantization noise I could get out of it? Well, it's just this formula for epsilon squared that we just talked about. And we just said that that goes as, did I lose a power of 2? Well, dimensionally, this matches this, but this doesn't match that. So this is the noise density per unit volt. It is left as an exercise for the student to correct this formula. I think what I have to do is actually divide that formula by the full range of the A to D in order to get it to come out right. So I think that's probably what's going on, which would imply that in this formula that we would actually have another factor of this dividing this up in the numerator. So I need to go check my numbers, but basically what this comes down to, I'll check it, but I think this answer may still be correct, is that it's equal to the maximum signal-to-noise ratio is equal to 12 times 2 to the n minus 1 for the number of bits you have. So for example, if I now express this in dB, I have 11 dB of signal-to-noise ratio plus 6 times the number of bits. So even if I have a 2-bit digital to analog converter, I have actually a very high signal-to-noise ratio in terms of just the quantization error. So when you use one of the scopes up in C105 and you're getting digital data off of it, what do you guys typically like to do when you're measuring signals on those scopes? Because if it's giving you digital data, you don't really care what it looks like on the screen. You're just trying to get the digital data off of it to process, right? So would you bother adjusting what the waveform looks like on the screen in order to get the digital data out of it? How many of you have pulled digital data off one of those scopes using LabVIEW or something? You guys do that as a electronics class exercise anymore? Kinda? Okay. So, sorry, I'm taking side turns and coming back here. So on a scope like that, does it matter if you're trying to make the signal big or not? Turns out the answer is yeah, it does. Because the scopes, what they actually do is those are 8-bit scopes. They quantize the display into 8 bits. But it's the display size that determines the range of the A to D converter. And so if you have some teeny little signal that's only taking up a centimeter or so of that 10-centimeter display, you're actually not using the last couple of bits, at least the last couple of bits of the display. So whenever you're using a digitizing oscilloscope and you're pulling data off of it to analyze, if you want the best quality data, you need to fill the display with the signal. All right? Dithering is related to trying to stay out of bad spots in terms of quantization error. So if I was measuring just right at this blue signal, again, I would have a fairly high quantization error. I would actually be better off to take that signal and put a little bit of AC sinusoidal modulation on it and move it back and forth. And then sometimes it would be on this step up here, and sometimes it would be on this step down here, and I could actually average those two steps in time, saying, okay, well, it's bouncing back and forth between two different readings, between a voltage of 2 and a voltage of 3, so I'm going to just average those. And it would spend more time on 2 than it would spend on 3. And if I average those, then I can actually find out more accurately what the value is here than if I was just believing just this level or just this level. That notion of adding a little signal to it and bouncing it around so that you don't get stuck in a bad region in the quantization error is called dithering. So dithering is this notion of providing a small AC modulation to a primarily DC or slowly varying signal in order to get the more accurate reading off of it. Does that make sense? So that's dithering. I think that's it. That's my exciting lecture on quantization noise so far. Yeah, we're going to talk about one other thing today before we go. Any questions about quantization error? What's the most bits any of you have ever used in an A to D converter for a measurement? Anybody have a 16-bit A to D converter they've used? Minghao, what, more than 16? 24? 16? Okay. And so, how many bits were you actually using all 16 bits of the quantization scale on your measurement? You never thought, I'm sorry. Okay. It's interesting to go through I was doing a project on a biosensor, a fluorescence biosensor, a decade or more ago, and I had a student who kept wanting to buy better and better A to D converters. And they weren't doing anything for the measurement because there was so much thermal noise that the thermal noise was 20 or 30 times what the quantization error was even on the 8-bit converter. So, all right, what else do I want to talk to you about? I want to talk to you about receiver operating characteristic curves. So first of all, I want to define another version of sensitivity. What's the version of sensitivity we've already defined in this class? Remember that? So the limit of detection is a value that's kind of the smallest amount of something that you think you can distinguish from a blank with a certain amount of certainty. What is, but that's not what we call the sensitivity. The sensitivity is when we had a sensor that had a characteristic where there was maybe some concentration of some molecule we were trying to measure, and there was an output voltage, and the blank value was when we have a 0 concentration, but then there was the slope to this. And the slope was the sensitivity, and that's the word for sensitivity that's used in a chemical context. So if you're talking to a chemist or a chemical engineer, and they're using the IUPAC, International Union of Pure and Applied Chemistry definitions, that's what they mean by sensitivity. Turns out if you're doing medical diagnostics, people mean something else in terms of sensitivity. So whenever you hear the word sensitivity, you might say, is it obvious to me from the context what they're talking about? So for example, are the units something like volts per mole or nanomole or something like that? Well, then that's probably this line slope they're talking about. But if they're saying that the sensitivity is 98%, that's not what they're talking about. They're talking about what we're going to talk about here. So first of all, I want to define the terms true positive, false negative, and true negative, which is what these abbreviations here stand for. So, any of you ever taken one of those rapid strep tests when you go into the doctor's office and they swab your throat and say, we'll have the answer for you in about 5 or 10 minutes? Okay, and did your tests, if you don't mind talking about your personal health condition of strep throat, did your test turn up negative or positive? Okay. And then yours turned up negative, and then they say, fine, you're perfectly fine, we don't have to do anything else, I'm not going to prescribe you antibiotics. Oh, they did. They actually believed yours. Okay. Maybe they're getting better. For a long time, the doctors would do these tests, and then they'd say, yeah, I don't really trust this test, so we're going to send it out for a bacterial culture anyway, and in the meantime, I'm going to prescribe these antibiotics for you. So that's kind of a worthless test, and the insurance companies get really mad when you charge them for those kind of tests because the doctors aren't making any true decisions based on them. So in that case of the rapid strep test, we might think about a matrix like this for talking about what the rapid test is telling us, but our gold standard, the thing we might really believe and trust in, would be the bacterial culture that they would do in the lab. The trouble is the bacterial culture takes 4 days or something like that to get and read the results of. And so they don't want your infection to get worse while they're waiting for the results. That's a lot of times why they don't why they don't respond to it. So whenever we talk about this type of matrix, it automatically assumes there are 2 tests for the same thing going on. one you're not sure about, and one you really, really, really trust, okay? And we're going to take the one that we really, really, really trust as truth, whether it's true or whether it's absolutely right or not. We're going to take it as truth. So a true positive is when our new, maybe less well-characterized test tells us you have strep throat, and the gold standard, the culture, also tells you you have strep throat. So it's telling you you're positive for strep and that this is actually correct. A false positive is where you don't have strep throat, but the rapid, as determined by the culture, but the rapid test tells you that you're okay. So you really, I'm sorry, I probably didn't say that right. The culture says you don't have it, but the test says that you do have it. So it's telling you you're positive, but it's false. So that's not correct. On the other hand, if our new rapid test is negative, we're going to fall in one of these two categories. We're either going to have a false negative, meaning that we missed your disease, or we're going to have a true negative, meaning you don't have the disease and our test tells you that you don't have the disease. So those are the definitions of those. In this case, sensitivity is defined by all the cases where the patient truly has the disease. How many of them do you find? So if the patient truly has the disease, we're in this column. And we find these ones we find, but these ones we miss. So if I take this and I divide it by the total number of patients with the disease, that tells me how sensitive the diagnostic is. So for example, if there are 100 people that have strep throat, I give them the rapid test, it finds 98 of them, says that 98 of them have strep, 2 of them don't. That test is 98% sensitive, okay? The other quantity that people care about is the specificity. And specificity is defined as the ability to tell somebody they don't have something or they have something different when they do. So in this case, what we're going to do is we're not going to look at this column for patients with disease. We're going to look at this column for patients without disease. So they don't have strep throat based on bacterial culture, but we're going to find out how many times that's really true. So let's say we had 50 patients. They all tested. None of them had the disease. 48 of them were told they don't have the disease by the test, but in some cases I had some false positive. I had 2 of those. Well, in that case, I would have 4% wrong answers, so my specificity would be 96%. All right? Any questions about these basic definitions of false and true positives and negatives, or sensitivity and specificity? So I may have started this discussion with you in another class period, but what's more important, to have a test that is sensitive or a test that is specific? Ming Hao? Right, based on the consequences. So let's say you have a test for gangrene, all right, to find out if you have gangrene in a limb and it needs to be amputated. What are the consequences of not amputating? The patient dies, okay? What are the consequences of amputating when it's not really true? You take a limb off a person. So both pretty dire consequences. And in a case like that, you'd really have to think through how to balance those out. Have any of you taken systems engineering classes here? They've kind of fallen out of favor, I guess, since I don't think we give people credit for some of them anymore. Have you taken them? Yeah, I'm talking about the systems engineering classes, which do things like risk analysis and that sort of stuff. Okay. Let's do a more current example. You have an ultrasound test for fractures in jet engine blades. What's important? sensitivity or specificity or both? What are the consequences? How would you balance it off? Yeah, so to put it in context, there's a recent crash where on a engine that was a combined joint project between GE and some other company, I don't remember, there was a crack in one of the turbine blades on the jet engine, and in flight at 35,000 feet or something, the blade broke off, and unfortunately in this case, parts of it shot into the cabin and knocked out a window, and I still don't know exactly what happened. I think some of the blade must have hit the person sitting next to the window. Anybody know the details of what killed the person? Yeah, I know they got partially sucked out, but then they got drugged back in, so. Oh, they suffocated. Wow, okay. So, killed a person, and as a result, the FAA ordered additional tests on all of these things. Now, as a jet engine manufacturer, you have to decide how much testing you're going to do on a jet engine before you put it up there, or as an airline that has them in practice, how much you're going to pay for maintenance to keep those up there. So how do you make the right decision about how to balance how much testing you should do? Sure. What the probability for failure is comes into it, and the longer the engine goes, the higher the probability. Should you make a test that is absolutely 100% sensitive so that every single possible fracture that you would ever have would be caught? As people that are empathetic for others, you'd kind of hope that was the case. But I'm going to break your bubble and tell you that the way the world works is that actuaries have a table that tells them what the cost of a person's life is. And I was told this, I don't know, 20 years ago that it was $1 million. I'm guessing we're all worth more than $1 million now. And it was basically, what would the cost of the airline be of killing somebody? And they balance that off against what the cost and lost revenue of having more inspection time for the jet engine fleet is. So you would balance off how you're going to trade those off. Now, there's some curves that are used to talk about how dire that trade-off is in terms of a receiver operating characteristic curve. And so that's what this slide is talking about. So I want you to imagine that the negative cases that we have are shown by this bell curve up here. So in our sensors, you might imagine that this is the reading for a negative, but there's a bunch of noise on it that kind of smears it out, okay? The upper bell curve, shown in red to the right, is what the distribution of readings is if there's a positive. So let's say that this is a cracked jet engine blade, and this is a fine jet engine blade, okay, no cracked. And in terms of the signal strength of the ultrasound that comes off of that inspection, we're going to get different levels of reading. And the question is, okay, I need to draw a line someplace, and I need to say, if I get an ultrasound reading above it, that I'm not going to fly the plane. And if I have an ultrasound reading below it, that I'm going to say it's okay. Where do I put the line, and how does where I draw the line affect the sensitivity and the specificity, okay? Imagine that you had a world's most horrible test that could tell no difference between whether it was cracked or not, okay? In that case, these two curves would lie right on top of each other, and based on the fact that the true negatives are the ones below the line and the false positives are the one above the line, if you look at how these fall out, if these two curves were dead on top of each other and I swept this line through for different thresholds, I would be able to trade off, I would be able to actually get a 100% sensitive test to detect every single crack. You know how I do it? I would just stick the threshold down here and say everything's a crack, all right? But it would have 0% specificity if that was the case. It would be easily fooled into that. Question?
I didn't see that that was 1 minus.
Right. I'm flipping this axis by writing it as 1 minus specificity, okay? So if the two curves are on top of each other, I get a straight line going from this corner up to that corner, and that's considered to be a diagnostic test that is worthless. There is no diagnostic value of that test because it can't have any distinguishing between these two. As these curves split apart, the curve starts to take some arc to it as I slide the threshold through it. And so I get tests that have some sensitivity while still maintaining 1 minus specificity near 0, that is specificity near 100%, okay? And ideally, where I'd like to get to is I'd like to get to this corner. In this corner, I have 100% sensitive and 100% specific test. That would require these two to be so well separated I can draw a threshold between them and none of the tails overlap on it. And so I could look at how much these overlap by using some statistics. So I want to show you some data that's, and this is called a receiver operating characteristic curve. And again, the history was, this is birds, this is German bombers. And if you have a radar, very early radar, how do you decide where you're going to put the line between these? Do you scramble your fighters every time there's some teeny little blip over Dover? Or do you say, nah, and then occasionally have the lone bomber come over and drop something? So that was the original reason for coming for it. So receiver comes from the idea of having a radar receiver. So, but it gets used in all sorts of applications. So this is some data from a paper that I published with a grad student. Again, it seems like everything's a decade ago. Where we were looking at the difference between a cancer called hemangiosarcoma and white blood cells. So we took we were effectively mimicking a test called a circulating tumor cell test, where you take a blood draw, you spin the blood down, you separate the white or blood cells or leukocytes from all the red blood cells, you blow up the red blood cells so that they're not even there. And then you look at the individual cells that are in the white ones, and some of them are actually cells that broke off a tumor in the body and were floating around through the blood system and could possibly land somewhere else and cause cancer. That's the pathway for metastatic cancer, when cancer spreads from one organ to another. So we came up and did this analysis and found these statistics that when we had cancer cells, they were spread out with a very loose Gaussian interpretation of the fit here for what they looked like. And the peripheral blood mononuclear cells, that is white cells or leukocytes, looked like this down here, had a much tighter distribution. And we were analyzing how good of our diagnostic was at being able to tell the difference between these two. So if you watch carefully, this blue line is going to move through these characteristic curves, drawing possible thresholds. And as the blue line moves, you're going to see that dot go through the graph to trace out what the different steps were. And unfortunately, I don't think I can freeze it in the middle. But the idea here is that basically we're never catching any cancer. So we're 0% sensitive to cancer, but we're not being fooled at all either. Okay? We're never calling something cancer that isn't, in fact. So the perfect diagnostic actually goes up into this corner, but there's still this trade-off that you can play with where you set the threshold to vary the test. So people talk about the quality of the test based on what the area under the curve is, or AUC. And AUC is basically what is the area under this curve where the dimensions of the box are 1 and 1. So if you have a perfect diagnostic test, you have an area under the curve of 1. If you have a worthless diagnostic test, you have an area under the curve, or AUC, of 0.5. And in between, you have something else. So I don't know if we wrote down what our AUC was on this, but it was something like 0.98 for this. Okay? So if you hear people talking about just the sensitivity or just the specificity of some diagnostic test, a reasonable question to ask them is, well, in terms of trading those off, what's your area under the curve? And then when they look at you, area under curve, what do you mean the area under the curve? You can go on and tell them about the ROC analysis. I want to tie this in just very briefly with one last statistical. Oh, there, if I just click enough, I guess it tells me these things. So we got to a point where we were 95% sensitive to these cancer cells, and we were 98 specific. That is, we only got fooled by another cell 2% of the time, based on these projected overlaps in these. So the area under the curve was 0.98. Now, I'll tell you, it turns out that that was nowhere good enough for what we were doing. And the reason why was when you're looking for these rare cells, you're looking for something like 10 cancer cells out of, even after you blow up all the red cells, 10 million white cells. And so it turns out that if I run 10 million white cells through this, and I have a specificity of 98%, it's going to think, don't make me do this math in public, 200,000 of them are cancer cells. Compare that to the actual 10 cancer cells I have in there. Even if I have a good chance of, even if I put in 10 cancer cells, I catch 9.5 of them. So I can't really tell those things apart. So on a cell-by-cell test, this sounds great, but actually in an application where I have a very rare cell event, it's hard to make that work. Actually, I don't think I'm going to go there today, but how many of you know about Student's t-test? Maybe I should go there then. I want to talk about these overlapping distributions and one other thing, which is whether you can really tell if these are two different populations or if they might just be one population, and you happen to have randomly sampled them in such a way that you didn't catch that. So this is just a normal Gaussian curve, the kind of thing that you've seen before, and you see what, based on how many standard deviations we are off of something, what the possibility of it occurring is, okay? By the way, when we integrate this function, we get something, we get the error function that I think we've talked about, okay? Data can be collected in sampling measurements that test a hypothesis, such as the hypothesis, we can distinguish hemangiosarcoma from leukocytes. And that if the data is considered insignificant for that hypothesis, it means basically your observation could just randomly occur. There's some chance it could randomly show up and not really show that there's any difference between those two cell types. Or your statistical sampling of it could prove to be significant, that is, that it probably wouldn't have occurred randomly. You can never completely rule out that something happens randomly, but you can make it incredibly unlikely that it would have happened randomly, okay? And we can basically set up, using that Gaussian definition, a significance level in which we judge something to be significant, and that goes according to that formula there. So typical popular levels for the probability of something being significant kind of go by these numbers here. One of them is there is only a 5% chance that this is random data, okay? And you might think, wow, that doesn't sound that good, but people use that all the time, that there's only a 1 in 20 chance that my results are random, and that's usually good enough to get things published. In certain medical diagnostics, people are looking for better results, so that, for example, there's only a 1% chance that this could have randomly occurred, or sometimes even a 0.01% chance, and you can see that those correspond to getting further and further out on those curves. So where I'm leading to, and the final thing I want to communicate today, is about this p-value, in case you see somebody reporting probabilities of, or p-values of something. So basically what the p-value is it's the chance something happened just randomly. So if you hear that somebody has done a statistical test and the p-value is 0.01, that means that there's only a 1% chance that this data would have occurred randomly, and 99% chance that there's actually a significant difference between them. So I don't think I'm going to read through all of this, but basically the key is that when you're doing this, you hypothesize the so-called null hypothesis. And the null hypothesis is there is no difference between these two populations. Okay? There is no difference in the performance in this class based on whether you're an undergraduate student or a graduate student. That's the null hypothesis. And then by using statistics, I can calculate what the probability is that that hypothesis is true or not. If I'm trying to prove that there's a difference between graduate students and all those extra years in tuition have made you so much smarter than the undergraduate students, then I want that probability to be low. I want it to be a low probability that there's no difference. So usually good statistical results have low p-values. So to do this, and I'm not going to go through the math, what you do is you use something that's called a t-test. And this was invented by a guy whose last name was apparently Student. And so it's Student's t-test. And it basically looks at having two distributions. No, didn't put it in here. Two distributions that look like that receiver operating characteristic curve, the way we just looked at, that are overlapping. And it's a function of how far apart the two mean values are for these, and also what the standard deviation of each one of these is. And depending on how far the means are separated compared to the sum of the squares of the standard deviation, you can figure out what the probability is that you're on the other side of, that you're statistically significant. So this is obviously related to the receiver operating characteristic curve. So with that, and the next class is ready to come in, I think I'm going to stop. Last class will be on Thursday. I don't really have any additional material I want to cover with you. Bring questions, bring examples, bring your homework, and we'll see you on Thursday.